Hola, my name is Pamela. Welcome to my channel. Today I'm gonna talk about total radiation pyrometers are made of a Pyrex, silica or calcium fluoride lens that concentrates the radiation from the hot object in a thermopile made up of several PTRH thermocouples of small dimensions and mounted in series. The radiation is focused hitting the hot junctions of the thermocouples directly. Their low mass makes them very sensitive to small variations in radiant energy, and moreover, very resistant to vibrations or shocks. The part of the thermocouples exposed to radiation is blackened, and this is to behave like a black body, thus increasing its energy absorption properties and providing the maximum EMF. The EMF provided by the thermopile depends on the temperature difference between the hot junction, radiation from the focused object, and the cold junction, and it is compensated by a nickel resistor connected in parallel with the pyrometer connection terminals and placed inside it, so that its temperature is always equal to that of its body. As the ambient temperature increases, the resistance value of the nickel coil increases, which compensates for the loss of EMF of the thermopile that accompanies the heating of the instrument's body. The compensation described is used for maximum ambient temperatures of 120 Celsius. At higher temperatures, air or water cooling devices are used, which lower the case temperature by about 10 to 40 degrees below ambient temperature. The pyrometer can have a rear lens to correctly focus the radiation on the thermopile, an automatic safety device to isolate the lens from the process and protect the pyrometer in the event that a flame reaches it directly, and the following accessories. Air cooling device, which protects the lens against excessive heating and at the same time keeps it clean from gases or vapors that may be in contact with the sight tube. Water cooling device, usually used with the air cooling device. This accessory prevents the body of the pyrometer from becoming excessively hot by conduction along the sight tube or by radiation from other sources. Sight tubes with open ends, used to protect the lens or to prevent the arrival of radiation from other foreign sources at which it is aimed. Sight tubes with closed ends, which are used in furnaces with a pressurized atmosphere or with particularly aggressive gases, and in the temperature measurements of molten metals, in which the sight tube must be submerged due to the existence of a slag on the surface metal, which would result in a wrong reading temperature. The bottom of the tube is the source of radiation, and the side walls have little influence. As the tube is closed, the working conditions are close to those of a black body. The protection tubes of radiation pyrometers can be metallic or ceramic. The former are made of stainless steel or metal alloys resistant to heat and corrosion, and are used at temperatures that generally do not exceed 1100 Celsius. They allow a faster response to temperature changes than ceramic tubes. In this table, we can see the characteristics of these tubes. Alloys resistant to high temperature corrosion and molten salts. Ceramic tubes are used up to 1650 Celsius and can be seen in this table, where the maximum temperature of each type of material of ceramic protection tubes is shown. The most used ceramic tubes are made of silicon carbide, which is widely used in furnaces, as it has good thermal characteristics, quick response to temperature variations, and resistance to sudden changes in temperature. And ceramic, which is a verified refractory material which at high temperatures presents great resistance to thermal shock and the penetration of gases present in the furnace, but has low mechanical resistance. For its reasons, this tube should be used with caution. In the heat treatment in salt baths, it is advisable to start up, heat slowly, and submerge at low speed. About 25 millimeters per minute is recommended to avoid a sudden thermal shock that would lead it to its breakage. After a few dives, it needs to be replaced. The relationship between the electromotive force generated and the body temperature is independent of the distance between the body and the lens. Excluding the presence of energy-absorbing gases or vapors, provided that the image of the radiation-emitting body surface completely covers the thermophile hot junction. The manufacturer standardizes the relationship between the dimensions of the object and its distance from the lens to guarantee good reading conditions. Thus, there are narrow-angle radiation pyrometers with a distance factor of 20:1 and a wide-angle pyrometer with a distance factor of 7:1. A problem of great importance is the selection of the lens material that must transmit the maximum energy compatible with the range of radiation emitted. Pyrex lenses are used in the temperature range of 850 to 1750 Celsius. Fused silica lens in the range of 450 to 1250 Celsius, and calcium fluoride lens for lower temperatures. In this graph, we can see the distribution of radiant energy. It can be seen that the visible radiation represents the area between 0.4 and 0.75 microns. That Pyrex lenses allow the passage of waves from 0.3 to 2.7 microns. That those of fused silica allow waves of 0.3 to 3.5 microns to pass through, and that of calcium fluoride, they do so up to 12 microns. Also, non-luminous flames radiate and absorb energy in a broad band of 2.4 to 3.2 microns due to the presence of CO2 and water vapor. In this way, the use of the Pyrex lens eliminates practically all the wavelengths corresponding to the energy radiated by CO2 and water vapor, and therefore, the temperature measurement is not influenced by the presence of non-luminous flames. However, a pyrometer with a silica lens that passes waves between 0.3 and 3.8 microns is sensitive to radiation from non-luminous flame if it interferes with the line of sight of the instrument. Likewise, a special pyrometer made up of a calcium fluoride lens and with a wide focus angle to capture as much energy as possible, which is very weak at low temperature, allows measuring very low temperatures from 50 to 200 Celsius. Here we can see some of the industrial applications of radiation pyrometers. And well, this will be all for today's video. Don't forget to give me a like, subscribe, and share. I upload videos every Wednesday in Spanish and every Friday in English. Adios! Exposed to radiation about 25 millimeters to avoid radiation emitting a body of